In this video, we'll be talking about evaluating acid and base strength from structure. And there are a number of ways that we can do that and talk about that. So in a very basic or very simple sense, an acid, the H plus comes off, and a base wants to pick up an H plus. Okay, so when we're trying to evaluate the strength of an acid or the strength of a base, we want to look at how easily does the hydrogen come off, or how strongly will the molecule attract a hydrogen. So I'm going to draw a structure here, and we're going to learn more about this particular type of drawing at the end of the semester. But a symbolized drawing for acetic acid looks like this. Okay, and basically, just to explain really quick, that means that there's a carbon right there and a carbon right there, and there's hydrogens coming off of that carbon. Okay, but what we're focused on evaluating based on structure is this bond, right? How strong is this bond? Okay, because that hydrogen is going to come off, right? And in order for that hydrogen to come off, that bond has to break. So if that bond is really strong, that hydrogen is not going to come off very easily, and it's going to be a weak acid. Right? So that strong bond there is going to be a weak acid. A weak bond there will be a stronger acid. Okay, so if it's a weak bond, then that hydrogen comes off easily, and the more ease with which the hydrogen comes off, the stronger the acid. Okay, so looking at structure, so one of the first things that we can evaluate is atomic orbital overlap. So atomic orbitals have a huge effect. To use a very scientific term, huge. So to illustrate this, let's look at two different molecules. One is H2S, and the other one is H2O. Okay, so we want to focus on how strong are one of these bonds. So when I'm talking about orbital overlap, my S is in the 3 shell, and my hydrogen is in the 1 shell, right? So not a great energy overlap, right? So a 3 shell has a lot more energy in its outer shell than a 1 shell does. Okay, not a very good orbital overlap. But with my water molecule, oxygen is in the 2 shell versus a 1 shell. So we have better energy overlap. Right? So not a great energy overlap. It's going to be a weaker bond. Better energy overlap will be a stronger bond. Okay, so our pKa for H2S, where am I going to put it? pKa for H2S is 7.0, and pKa for H2O is 15.7. Remember, lower pKa is a stronger acid. Right? This also means, so remember what we said about conjugates in the previous video. So thinking about the conjugates of these two things, if I have HS not an S, that's a triangle, HS minus versus HO minus, or OH minus. Remember, the conjugate of the stronger acid will be a weaker base. And the conjugate of the weaker acid is a stronger base. You don't really get much stronger of a base than OH minus, to be short. Okay, so in comparing these two things, those concepts from the previous video of evaluating conjugate pairs based on acid or base strength still apply. So if I look at, there's sort of a trend that goes along here. I can look at it on the periodic table. So if I have HF, HCl, HBr, or HI, my stronger acids will be down here, and then my conjugates, F minus, Cl minus, Br minus, and I minus, my stronger bases will be up here. Right? And thinking about how this orbital overlap plays into this situation. My orbital overlap for HF, those guys are both in the F is in the 2 shell, the H is in the 1 shell, so they're very close in orbital energy. Versus iodine versus hydrogen, there's a much bigger difference between iodine's outer shell and hydrogen's outer shell. So this bond right here between iodine and hydrogen is very, very weak, right? So this is the weakest of the bonds in this list, which makes it the stronger acid. But then the stronger acid results in a weaker base. So our weaker acid will be a stronger base, okay? So if there's no big orbital overlap, let's take a look. If no big orbital difference, electronegativity comes into play. Okay, so and remembering the trend in electronegativity on the periodic table, right? Fluorine is the most electronegative, and then as you leave fluorine, things get less and less electronegative. So if I want to compare, these comparisons are usually the easiest way to go. If I want to compare, let's say, HOH and HF, right? So my value for the electronegativity of hydrogen is 2.1. Oxygen is 3.5. So we have an overall pull towards that oxygen of the electrons. My electronegativity down here, hydrogen's 2.1, fluorine is 4.0. This is almost an ionic bond. Okay, so we have a much greater pull towards the hydrogen. Hydrogen is hoarding all of the electrons, right? That makes this a weaker bond than it is in water. and we compare our pKa's, 15.7 versus the pKa for hydrofluoric acid is 3.2. Okay, so the bigger electronegativity difference, the weaker that bond to the hydrogen is going to be. And remember, a weaker bond results in a stronger acid. Let's look at a couple of other examples. Oops. Versus chlorine. Right? So we have our electronegativity for bromine is 2.8. And our electronegativity for chlorine is 3.0. So we'll have a definite pull towards the bromine, but a larger pull towards the chlorine. Our pKa's are 8.7 and 7.5. Okay, so the chlorine compound will be a stronger acid. The whole reason for this, when electronegativity is the issue, is that the greater the electronegativity, the electrons are going to be pulled towards the one with the electronegativity. So our chlorine and our bromine are pulling electrons away from this bond. Right? We're going away from this bond. Right? And that's why that bond is going to be weaker when the electronegativity is stronger. The next thing to consider is resonance. Okay, and remember, resonance, the idea of resonance is that we often show resonance structures as a double bond shifting from one place to the other. But the reality is that, both of those bonds, or however many bonds there are sharing that, are actually sharing equally those extra electrons. So it's not shifting back and forth like a light switch turning on and off, but really those electrons are spaced out. Okay, so resonance stabilizes a conjugate base. Okay, which makes the acid stronger. Okay, so remember, bases want to pick up a hydrogen. So if the base is very stable, it has less of a reason to pick up a hydrogen, which makes it a weaker base. If we have a weaker base as a conjugate, then the acid will be stronger acid. All right, so let's look at a couple of examples. So we've got our acetic acid, and it loses its proton. Right? And we have resonance, right? This double bond to the top oxygen can shift. And that balances, that sort of shares the load of that extra negative charge. Okay, if that negative charge had nowhere to go, it would want to take care of that negative charge by grabbing onto a hydrogen, right? But because the negative charge is shared between two bonds, it has less of a reason to grab onto a hydrogen to stabilize itself, right? So if we look at acetic acid versus something like methanol, that's ethanol, excuse me. It loses its hydrogen. And that's all it has, right? It has nowhere else to shift that negative charge. So no resonance possible here. So this is going to be a stronger base, resulting in this, the ethanol being a weaker acid. Right, and our pKa's, pKa for acetic was 4.7, pKa for ethanol is 19. So significant difference when resonance is a possibility. All right, so let's do a little prediction. So let's predict which will be a stronger acid. Right? Both of these have the ability to do resonance. Okay, if I pull that hydrogen off, then that double bond can help to share the extra negative charge. Great, cool. So resonance is not going to play into our decision. We're going to find that the trifluoro compound is a stronger acid. Okay, why? Because all of these fluorines are pulling all of the electrons in their direction. Okay, I've got 3 fluorines, which is the most electronegative element on the table. So the extra electronegativity pulls the electrons toward the fluorine. Equals a weaker OH bond. Okay, so our pKa for this particular compound, 0.23. It's a very strong acid, as opposed to our pKa for acetic acid, which was 4.7. Right, so resonance plays a part, electronegativity plays a part, difference in orbital overlap energies play a part. So organic bases tend to be the same way. Okay, so remember, a base wants to pick up a proton. Okay, so if it's got electrons sitting in one spot, it would really like to be able to pick up a proton to balance all that extra negative charge. So if a base is more stable, it will be a weaker base, right? So a strong base is one that really, really, really wants to pick up a proton. It has extra negative charge that it wants to get taken care of, so it's going to be searching around for a proton to pick up, so it's a stronger base. But if it's more stable, it can be like, no, not today, thanks. So let's take a look at a couple of examples of some common bases. All right, we have ammonia versus same molecule but replaced with a bromine. Okay, so thinking about what we know about electronegativity. Okay, so we have these electrons that are sitting right here with that nitrogen, right? On the ammonia, nitrogen is the more electronegative. So all of those electrons stay right around that nitrogen, right? With the bromine compound, on the other hand, Bromine is more electronegative than nitrogen is. So the bromine pulls those electrons away from the nitrogen and stabilizes the nitrogen. Okay, that stabilization means that this is less basic. Okay, the bromine pulls electrons away. So nitrogen doesn't need a proton. Right, our pKb's, right? Remember, pKb is the rating of base strength, and the lower pKb will be a stronger base. pKb for ammonia is 4.7. Our pKb for this compound is 7.6. Right, so a little bit more about structure. So let's take a look at a couple more compounds and talk about them. Versus the same compound, but with no double bonds. Right, let's think about what we know about resonance. So in our first compound, the compound on the left, we've got these double bonds in the ring. And those double bonds are moving all around that ring. They're not actually staying in place. So we have resonance here. And what happens when we have resonance? Resonance stabilizes things. Resonance stabilizes, so it's a weaker base. Okay, we've got these electrons that are sitting on this nitrogen right here. And if we didn't have resonance, that nitrogen would really like to have another hydrogen in order to take care of that negative charge. But since we have resonance in the ring, that ring helps to deal with that extra negative charge. It helps to pass around the buck, pass around the extra stuff that's going on. So we have a weaker base. It doesn't need the hydrogen as much. Right? Our pKb's for these compounds, pKb for this one is 9.1, and the pKb for the second compound is 3.4. Now our last topic in terms of evaluating strength or of bases is what happens when we start adding carbon groups. So if we start with ammonia again, it's a nice base to talk about. It's simple, but it illustrates a good point. What happens if I replace one of my hydrogens with a methyl group, a CH3? Right, what happens here is in the ammonia, our compound on the left, that one really likes to have another hydrogen on there to get rid of that extra negative charge. But when I add the carbon to the ammonia compound, the carbon actually donates electrons in the direction of the nitrogen. Right? Our ammonia has a pKb of 4.7. When we add that methyl group, that carbon group, that causes the pKb to drop. Right? If I force more electrons towards that nitrogen, it wants more to get rid of that extra negative charge, right? It has a stronger desire to grab a hydrogen in order to dissipate that negative charge. If I add another carbon group, it gets even worse. Now I've got two groups donating electrons towards my nitrogen, and our pKb for this one goes down even further, just by a bit. Okay, so adding carbon groups to a base gives us a stronger base. We say that carbon is electron donating. Right? And if we force more electrons into one particular area, that molecule really wants to grab a hydrogen in order to balance that stuff out. Now, the last topic for this video is a fairly short one, and it's about our third version of the acid-base theories. Right, we talked about the Arrhenius theory, we've talked about the Bronsted-Lowry theory, and now we're going to talk about Lewis acids and bases. Right? So with the Bronsted-Lowry theory, we had proton donors and proton acceptors. With Lewis theory, Lewis acids are electron acceptors. And Lewis bases are electron donors. Right? Now this makes it actually kind of easy to identify a Lewis base, because in order to be a Lewis base, you must have lone pairs. To donate. Right, that's where the electrons get donated from, is if a molecule has some lone pairs on an atom. So let's look at an example. So if I have some hydrofluoric acid plus some water, and remember that water has some lone pairs on that oxygen, we'll get some F- and some H3O+, right? Hydrofluoric acid plus water gives us some hydronium ion. And what happens here is that because we have lone pairs, it donates electrons to the fluorine. Making it a Lewis base. The water is the Lewis base. Okay? The fluorine accepts the electrons, making it a Lewis acid. Right? It also is the proton donor, which makes it a Bronsted-Lowry acid, right? But the easy thing about that is being able to identify the Lewis base because of the lone pairs in that molecule. So being able to draw molecules accurately and making sure you know where lone pairs go is important to determining whether or not something is a Lewis acid or base. Now, the other important aspect about the Lewis acid-base thing is that the electrons do not come from the outside atoms. Okay, we need lone pairs on a central atom. And what the result of this particular reaction looks like is this. Right? So we make a bond between the nitrogen and the bromine. But both of the electrons in that bond are from the nitrogen. Right? And we can identify the ammonia as the Lewis base because we have lone pairs. Right? So the ammonia is the Lewis acid. That makes the bromine compound the Lewis base. Right? So we can deal with acid and base behavior even when we're not dealing with proton movement. Right? No protons traded hands in this particular reaction, but it's still an acid-base reaction. All right, that's going to do it for this particular video. When we return, probably for our last video, we'll be talking about finding the pH of weak acids and bases, and that's going to take us right back into ice table land. Yay! Have fun!